Excellent. Well, it's a great pleasure to have Michal Heller visiting virtually from, not from Hanover as I announced, but from Potsdam. I looked up the wrong location for the Albert Einstein Institute. There are two branches apparently, he was explaining to me. So I'll correct that on our website. So thank you for joining us, and without further ado, I'll hand over the floor to you.
Okay, very good. Thank you, Daniel, for the invitation. It's a pleasure to be virtually present and give this talk. I've never been to Ireland. My wife was, and she told me it's
really you must come and visit us, yeah.
What I want to tell you is a really interdisciplinary talk, as you will see, that is based on a series of works that I did with members of my group, Gravity, Quantum Field and Information in Potsdam, as well as many other collaborators in the course of the past 3 years. And basically the topic is complexity and quantum field theory. So let me start with a brief introduction. So as I tried to announce before, this talk is going to be very interdisciplinary, and it's because it's based on an emerging principle or an emerging viewpoint of seeing fundamental interactions. I mean, gravity, strong force, etc., and also what lies behind them through quantum many-body lenses. And when I say this, I mean various things, and I think like all these things that I'm going to mention here appear in my talk. So of course, on one hand, when we talk about fundamental interactions, what we can do is we can consider collective states of fundamental interactions. And the collective state that I really have in mind is a corroborate plasma probed at RIG and LHC accelerators. And over here is a sample plot of how this new state of matter is described using viscous hydrodynamics with some shear viscosity, etc., etc. Then it's a non-equilibrium process in quantum field theory, and one of the things that you can do, and this is also another thing that we do in Potsdam, is to use tensor network techniques, so representing quantum many-body states in an efficient, certain quantum many-body states in an efficient way on classical computers and simulating them ab initio. And so these are tensor networks, and using these tensor networks to obtain interesting results about quantum field theory. Then another quantum many-body aspect of fundamental interactions is holography, also known as ADS-CFT, in which we think about gravity as emerging from, say, collective states in quantum field theory, or say black holes emerging from collective states in corresponding quantum field theories living on a boundary. And the last aspect, and this is what I will be basically talking about using various techniques from these three other corners, is the idea that, well, in quantum mechanical systems, including quantum field theories, when one is interested in states, there might be various ways of preparing the same or approximately the same state, right? So such a freedom of different ways of state preparation is something that one can utilize to one's benefit. And actually, this is precisely what the story of complexity in quantum field theory is going to be. And as I said, this talk is going to be very interdisciplinary because these various ideas are going to appear over and over again in various incarnations to the benefit of our understanding. And of course, I have not said it at the beginning, but please interrupt me whenever you have questions or comments. I know that you're a broad audience, so my aim for this talk is try to give you an idea what this new field of complexity in quantum field theory really is, and what are the motivations for this field, what are some sample development, and why the future is bright for these kind of considerations. So the common topic between these four aspects of quantum many-body physics of fundamental interactions is the notion of entanglement. So to what degree a bipartite quantum system is not in a product state. And actually this notion of entanglement and its entropy, fundamental entropy, specifies how difficult it is for a given quantum state to be represented on a classical computer as a tensor network. Right, so tensor networks are variational ansatz in which one views a many-body wave function as a product of matrices. And this way of representing wave function allows to manipulate efficiently with it on computers that are at our disposal, including computers like the laptop I'm speaking from. So one kind of tensor network that is actually not going to be of much interest to us, but was used in the periodic transparency, is the so-called matrix product state tensor network. And the other one, actually, the one that's going to be of interest to us, is called multi-scale entanglement normalization ansatz tensor network. And this is a tensor network that is capable of representing or approximately accurately a ground state of a critical system, so a system with long-range entanglement. And this tensor network can be actually thought of as a quantum circuit, so a unitary transformation that is composed from smaller unitary building blocks. And this transformation contains two kinds of unitaries. There's a unitary that has sort of four legs and acts really as a unitary acting on another layer on the circuit. And this another kind of a unitary that basically that has one leg connected to a product state that lies at the beginning of the circuit, right? So this mirror tensor network is nothing else than actually a unitary circuit that acts on a product state, and so state without spatial entanglement, and it's constructed in such a way that upon acting with enough number of layers, we reproduce approximately the ground state of a critical model. And it is supposed to be considered as variational ansatz, right? So it's actually a numerical algorithm that allows you to simulate a ground state of critical lattice systems on classical computers. The important thing for us is that it's a unitary circuit. There's a product state on which you act, and then the rest is a complicated unitary transformation that is composed from smaller building blocks. So
these unitary, excuse me, could I interrupt? These unitary transformations, they have to be tuned to the model, or how does it work? They're not all the same, right?
Very good. They have to be tuned to the model, and initially, so this tensor network was born around 2005, and initially it was really a variational ansatz, such that somebody gives you a lattice Hamiltonian, say a Ising spin chain at criticality, and you're supposed to run numerical algorithm in which you variationally minimize the expectation value of the energy to get the ground state, and in this way you determine all these tensors. Of course, there are symmetries that you can impose, right? For example, if the system is critical, then every layer should be the same because of the scaling variance, right? So in the end, like, you're working basically with two types of tensors, right? But it's a numerical procedure, and in the course of the past several years, there's been more analytic progress in understanding this tensor network. It's somewhat relevant for what I'm going to say, but if time permits, I may give you an upshot towards the end of my talk.
Just if I might ask as well, what it has been used for the Ising model, but at criticality, one of the problems tends to be critical slowing down in numerical simulations. Does this help with that?
Yeah.
Well, this tensor network can be simulated on a classical computer. There are examples in which the models were solved. The ground states were found for various critical systems that in the infrared are described by conformal field theories. I think what's fair to say is that the minimization or obtaining tensors from anything minimization or other algorithms in this case is computationally more costly than doing this simulation.
Okay.
And more tricky. But otherwise, it's just an algorithm. It's part of the literature now.
And is there any sense in which you can get the exact critical exponents for such critical systems?
So there's a,
or are you approximating them? Because
so you're going to be, I mean, because it's a numerical algorithm, you're always approximating critical exponents, so scaling dimension of operators. But there is an incarnation of this network that is basically semi-analytic, that is based on wavelets. It's a paper by Steve White and Glenn Everly, I think from 2017. So there's something in between numerics and analytics that exists in the literature. And it's only for the Ising model, I think. Good. So let me proceed. So these are tensor networks. What I want to emphasize is that past year 2004, there existed actually many results on entanglement entropy in quantum field theory. And in particular, there exist universal results and tools in two-dimensional conformal field theories. And now in ADS-CFT, what turns out, so ADS-CFT is, of course, the duality between quantum gravity in d+1 dimension and quantum field theories in d dimension on the boundary. It turns out that entanglement entropy is nothing else than the Bekenstein-Hawking entropy of certain codimension two surfaces. And well, the idea is that if you consider a state in your holographic quantum field theory, the state is specified by a constant time slice on the boundary. So here, this is this dashed region. On this constant time slice, we pick a subregion. So I mean, the state here is going to be the vacuum. The subregion for us is going to be like this part, like this A. Then it turns out that if we consider a codimension 2 minimal surface that is anchored on the boundary of the subregion on the asymptotic boundary of ADS, then the area of this magenta object measured in terms of 4G Newton is going to give us the fundamental entropy of the reduced density matrix. And this is this was a conjecture by Yu and Takayanagi from 2006 that was largely based on universal results for entanglement entropy in two-dimensional conformal field theories delivering around 2004 and earlier. That was later proven by Lukovic and Molosena. And now it became a new quantitative tool for quantum gravity, and it's behind, in particular, a recent discussion of islands and the resolution of the Hawking paradox using ADS-CFT. So what I want to emphasize is that entanglement in the context of ADS, anti-de-Sitter quantum gravity, is actually rather well understood. And what my talk is about are new quantum gravity observables that are very simple to understand, yet they were introduced to this literature only from between 2014 and 2016, so relatively recently, about 5 years ago. So the idea behind these observables is basically the same as for entanglement entropy. That is, we have anti-de-Sitter solution, right? And we're talking about gravitational theory, right? So in the gravitational theory, the only observables are the ones that are defined in a diffeomorphism invariant way. And as a result, on the gravity side, we want, and what's important is that in the context of ADS-CFT, in ADS spacetime, we have this asymptotic boundary. And basically on this asymptotic boundary, right, like when we pick a time slice, as I said earlier, we pick a state in a dual quantum field theory. So suppose that again, we pick a state, right? And now we have this constant time slice on the boundary. And in order to define something that is diff invariant in the bulk of ADS, what we can do is to consider either, codimension one object. So, basically soap bubble volume that is spanned on this constant time slice on the boundary. And in order to get the unique one, what you need to do is you need to maximize the volume in the Lorentzian case. So basically the new observable is a volume of codimension 1, maximum volume bulk time slice. Or the other choice is to consider this constant time slice on the boundary, shoot light rays to the future and to the past inside, and this defines for you this causal diamond. And once you have this causally defined region, you can do two things. You can either evaluate gravitational action inside, or you can actually, and this is this case, or what you can do is you can calculate the space-time volume inside this causally defined region, and that's basically this third observable. So I'm going to refer to these observables as CV, CA, and CV point to 0. Now, this was basically the case of the vacuum. You can apply the same logic to maximally extended anti-de-Sitter black hole, such spacetime has two asymptotic regions. So there are two times. So actually the pure state that corresponds to this geometry is the so-called thermophile double state. I mean, this is known from the work by Israel from the late 20th century. We have two times, so like we have to pick a time on the right, time on the left, right? And then what we can do is we can either consider the volume of maximal volume slice. So this is this orange part, or this causal diamond. What's important is that these two, what's important, what makes these observables interesting is that these codimension 1 and codimension 0 quantities naturally penetrate black hole horizon, and are interesting proxies of what's happening inside black hole. Now,
sorry to interrupt, but can you tell more about the geometry of this picture on the left, like when you have like two tessellations and one tessellation in the middle? So what is it modeling?
Okay, very good. So for the moment, let me finish this and let me answer this. Okay.
Yeah, you can answer this whenever you want. It's just what I thought that it was not completely clear for me, but I'm a more geometer, right? So
okay, so this is nothing else than empty anti-de-Sitter solution. So the constant time slice is a hyperbolic disk in d dimensions. So you should think of this geometry as a geometry that is made from constant time slices being hyperbolic disks, right? This is empty anti-de-Sitter geometry, and this is the black hole.
So the disk is so on the top, because what is the whole thing? What is like? It's so does it have to be an isometry? What it is at least like topological type of this whole thing?
So this is the time direction, and the time direction extends between minus and plus infinity, right? So this whole geometry is a cylinder, is an infinite cylinder, but with
so this was my question, because any case, if you look at something which is like has dimension d, you can look at the like d-1 whatever object, and then the d direction, it's a time, right? So that's why this was my question. So it's a cylinder, right? So it's a hyperbolic disk and a cylinder. Okay, thank you very much. It's very helpful.
Very good. So thanks for the question. So now, well, I mean, we have these quantities. So we have the volume of maximum volume time slice of codimension 1, the action in codimension 0 causally defined region, and the volume of causally defined region. And now we can evaluate it in these two solutions. So for empty EDS solution, basically what we get is that this first observable, as well as the last one, behaves as a volume occupied by the holographic quantum field theory, measured in the units of the UV regulator, so it's divergent. In the case of this action observable, it behaves as a volume occupied by the quantum field theory, so the volume of this time slice on the boundary, measured in the units of the UV regulator, times an additional logarithm. Now, in the black hole case, what you can do is you can calculate it for the black hole. You have two asymptotic regions. So what you can do is you can regulate it by subtracting twice what would be the answer for each empty ADS spacetime. And it turns out that if you do this at some fixed time, then what you get is that this difference is equal to the thermodynamic entropy, so the area of the horizon, of course. And now what's important and what's interesting is that we have like here two times. So it turns out that moving in time in such a way that we're moving downwards on one side and upwards on the other is actually an isometry of this black hole solution, because it's just a killing direction. But moving in time in such a way that on both sides we're going upwards is not. And what happens is that actually both of these quantities, so both codimension 1 quantity and codimension 0 quantity, grow effectively linearly as a function of time, right? So at some time, I mean, with time, they become arbitrarily big for a very long time, as long as we can trust the picture in which the classical geometry is the right description. So this is the motivation for my talk, because these new gravitational observables that appear in the context of holography between 2014 and 16 were conjectured to be related to a notion of hardness of state preparation in dual quantum field theory using limiting resources. And now it's time to answer your second question. So you asked like why there are two different tessellations. So it turns out that there is a conjecture in the literature that says that the constant time slice of anti-disperse solution, so a hyperbolic disk, is a representation of a tensor network, of this Mera tensor network that I had provided for you before. So over here, what I did is I put this Mera tensor network on top of this hyperbolic disk. And now, if you think about hardness of preparing a ground state using Mera as related to the number of tensors in Mera, right, the total number of nodes in this tensor network, then calculating the total number of nodes in this case corresponds to nothing else than calculating the volume of this constant time slice. So as a result, although it's based on a conjecture, this idea that these new gravity observables are related to hardness of state preparation in dual quantum field theories using limiting resources, I mean, there's some ground to it. It's not completely ad hoc. And these three gravity observables that I showed you, so volumes of maximal volume codimension 1 surfaces, the actions in causally defined regions, and the volumes of causally defined regions go under the name of three holographic complexity proposals. And now the important thing, and I'm going to make this parallel with entanglement entropy and holographic entanglement entropy over and over again, is that when Yu and Takayanagi in 2006 proposed what is the holographic interpretation of entanglement entropy, there was already some understanding of entanglement entropy in quantum field theory. However, when it comes to this notion of hardness of state preparation in quantum field theory, so complexity, at the moment these proposals were made, nothing was really known about it. So my group, and this is what I'm going to describe in this talk, so it is an opportunity to actually introduce the concept of complexity to quantum field theory and understand its properties. So what I'll be doing is I'll be motivated by these holographic complexity proposals, and I will try to propose a workable example of a notion of complexity that can be applied to at least certain quantum field theories, and try to compare the predictions with holographic complexity proposals, right? And I will be doing this gradually, going towards more and more interesting situations. So it's a good place to pause and ask if you have any questions.
Of course, I can ask you more about your picture. So again, like your pictures on the top and on the bottom, it really looks like there is some Coxeter group acting on it, right? So that you do have some kind of fundamental domain, but we know that saying such kind of explicit examples of Coxeter groups exist only like up to dimension like 4 or 5. So, and then theoretically that they cannot, you cannot have such a regular picture in the dimensions more than 19. It's like very old result of Weinberg. So that's why it's for me it's interesting. What are the dimensions? Because okay, now I understand that you say like core dimension, but then still what is the dimension of your cylinder, right? If you need some symmetries on the top of the bottom, then you have an upper bound.
Very good. So what I will be interested in are situations in which this geometry is AD is 3, so it's 3-dimensional, and basically AD is 5, so 5-dimensional. And because of string theory considerations, I will not be interested in dimensions higher than 7. So if AD is 7, it's going to be the highest dimensional case that it would make sense to consider on mathematical grounds.
I have 2 questions.
Please go ahead.
The first is, there are infinitely many hyperbolic manifolds, obviously. I can, for example, take one and connect a sum of this with some compact prime manifold and get another. Because the first question is, how do these considerations relate to this change in the hyperbolic manifold we're fitting here? And the second question is, are these observables local? Are they compatible with axioms of local quantum field theory?
Yes, very good. So, okay. So thanks for this question. So regarding the first question, the way I understood it is, what would happen if I consider different geometries here? So the geometry that I drew for you here is a geometry of empty anti-disturbed space, and such a geometry would correspond to basically, under the space-time picture of quantum field theory, it would correspond to the time development of the vacuum state in a conformal field theory in one dimension lower, which is defined on the boundary of the space. Of course, you can change geometry, right? And you can consider, for example, a geometry in which there would be a particle moving and propagating inside this ADS spacetime, and it can backreact gravitationally. And what this geometry would correspond then to would be a time development of some excited state in a dual conformal field theory, right? And as a result, if I think about the quantity that I'm defining here, this quantity is going to be associated with a constant time slice on the boundary. So it's going to be associated with an instantaneous state in a quantum field theory, whatever it is, being a vacuum, thermophile double state, or more complicated examples. So I hope that answers largely your first question. And regarding the second question, I call these quantities quantum gravity observables in a sense that these are quantities that are diffeomorphism that are defined in a gravitational theory in a diffeomorphism invariant way. However, the same can be said about entanglement entropy. That entanglement entropy is the holographic entanglement entropy. So Ryuta-Kayanagi surfaces. So these surfaces here are quantum gravity observables in a sense, or gravity observables in a sense that are diffeomorphism invariant objects living in some geometries. However, the entanglement entropy itself is not really an observable in a quantum field theory. It's not really an expectation value of an observable, right? Because it's not really a quantity that is linear in the state, right? It's there's a part that is linear in the state, but then it's an expectation value of the log of the density matrix, right? So it's not really an observable in a strict sense of this word. And I think the same can be said about complexity. And the fact that this quantity is divergent is another indication that probably you should not really think of it as an observable in a quantum field theory.
I mean, I'm not very clear. I mean, you are saying that they are diffeomorphism invariant, but are they, for example, in the bulk? Oh, in the bulk you have only a classical theory, or you have a quantum theory?
So these quantities are, as I described them, they are defined in a classical theory, maybe in the presence of quantum fields that was limited by Gaussian. So these are certainly classical, at best semi-classical observables, and of course we don't know what necessarily replaces them in the full quantum regime.
So one does not know whether a putative quantum theory of gravity inside in the bulk is compatible with locality, as stated here. By the way, the entropy is only defined by taking the state and restricting into the algebra of observables. Otherwise, there is no meaning. So one needs both to define an entropy. So my question somehow is revolving around, you say vacuum state at the beginning, but we know, for example, that the vacuum state on the Rindler wedge is not pure. Okay? Likewise here, what is the algebra of observables to which one is restricting the state?
So I mean, thanks for this question. I mean, it's an important question. It's a bit tangential to my talk. I would say that this, in holographic quantum field theory, this is probably something that is not really super well understood. I mean, these are very complicated theories. These are gauge theories. I mean, to some degree, this question motivated people to understand how to define entanglement entropy in gauge theories. There's been a series of papers around 2015 on this topic. I think I do not really have much to say, but it's a valid concern. I mean, like The way I define here the entanglement entropy is in terms of a reduced density matrix. But of course, this trait, I mean, one has to be careful. This trait in, say, gauge theories is not something that is easy to define. Instead, you should define this as a density matrix that is consistent with expectation values for some algebra observables. I do not want to go in this direction. I mean, it's not something that is relevant for my talk.
Okay.
But thanks for the question.
Just, if I might just ask with regard to your picture again, just in the old days, ADS was problematic because it had closed time like loops, but you are working on the covering space of
that's correct.
so
Yes. Yes.
Where would the fundamental cell of this be in your picture?
Well, naively, I would say that that corresponds to some part of time on the boundary. And I think like the essence of your question is how this extends into the bulk of ADS. And I don't really know. I mean, I would have to think about it and stare at the equation. But I mean, I see your point.
Okay, that's fine.
Yeah, thanks for the question. So let me move on in the off time, because I think I'm speaking almost 30 minutes by now.
So we are not overly strict on times. So.
Well, sure. But still, I'm like I sort of want to provide you with the punchline. So what I want to say is that from what I presented in the introduction, the important thing for me is that there are novel quantities in gravitational theories with ADS asymptotics, and you can in fact also define them without ADS asymptotics. And the question is, what is their dual physical interpretation, right? So similarly, we would like to have something similar to what happened with holographic entanglement entropy. So there are Rieter-Kanagi surfaces. There are well-defined observables in a gravitational theory in a sense of the homomorphism invariant. The invariants, and we want to understand, or people wanted to understand what they correspond to in field theory, and they succeeded. So now, complexity in quantum field theory is not really, it's not something that was defined at the moment. People made this association between the volumes and actions and hardness of state preparation. So what I want to show you is a framework that allows you to define such a quantity in quantum field theory, and then allows you to do calculations. And these calculations can be then compared with the predictions of what's happening in holography and try to see what's happening. So like that's roughly speaking the logic. So I was showing for you like these properties of these holographic complexity proposals, because in the end I want to compare to them and try to see if we can enhance our understanding of them. So let's consider a simple situation. So let's I mean, in all these situations, we're always going to have a target state. So the target state is the state that we are interested in. In the context of the empty ADS spacetime, it will be the vacuum of the conformal field theory. In the case of this thermophile double state corresponding to the black hole, it's going to be the thermophile double state. And now we want to have something that we're going to deem a simpler state. And now there's going to be a unitary transformation that's going to take us between this reference state and the target state. And this unitary transformation is going to be built from building blocks. And we want to assign a weight to different kinds of building blocks that appear there and try to find the optimal transformation according to our desires. So when presenting this topic, I very often use the example of a single spin. It turned out that last year, Brown and Saskind actually wrote a paper about this simple example. So now you can find details in this paper. So let me tell you the story. So imagine that somebody asks you to, you have one spin, and somebody asks you to prepare a spin pointing in the Z direction from a spin pointing along the X direction. So one way to do this would be by a rotation using a Pauling matrix along the Y-axis by an angle pi half. But of course, there are infinitely many transformations that you can do to transform this reference state into a target state. You can as well rotate first along the z-axis such that your reference state now points along the y direction, and then you can perform another rotation that brings you back to the target state that you wanted, right? So if I were to ask you what operation is simpler, then at least myself, naively, I would say that the first one is simple, then the second one. And if I were to tell you why, after thinking about it for some time, I would tell you that in the first case, we applied the Pauli matrix with an angle pi half. And in the second case, we did the same twice. So pi half is smaller than pi half plus pi half. So that's like what my intuition is telling me. But now, suppose that for some technical reason, the rotation along the y-axis is 10 times harder to do than the remaining rotations. Then if you were to follow this logic, you would put here a factor of 10. And now it turns out that this double rotation would be a simpler operation to perform than this single rotation. So what I'm trying to tell you is that what you call simple or what you call hard is a bit subjective, in a sense that you have to specify the rules of the game, and these rules of the game are going to tell you what is really the optimal transformation. So the important thing is that this approach to complexity was introduced in a somewhat different context by Michal in 2005. And the good news about it is that it naturally applies to quantum field theories. So instead of thinking about rotations by pi half, you can think about the continuous rotation. This rotation is going to be generated in the gradual in a gradual way as a circuit. So this unitary transformation here now is a circuit. The circuit is gonna, as a circuit, it has a layer structure, and each layer is generated by a sum of some Hermitian operators. And at each step of the circuit, a given Hermitian operator is invoked with a particular real number. And now, if you were to say how difficult it was to do that sort of an operation, what you would do is you would, first, sum absolute values of these numbers over a single layer of a circuit. Not all numbers have to come with the same weight. So these pi I here, this capital pi I, are weights with which you weight different directions in which you can go at each layer of the circuit. And now you still have to integrate over all layers. So these layers go from 0 to 1. And now the optimal circuit is going to be the one that minimizes this. And this quantity evaluated on the optimal circuit is going to what I will be calling complexity. And if you start at this equation, you see that it's nothing else than basically assigning an L1 norm to the vector form from number of times you apply a given Hermitian operator in a layer of a circuit. And you don't have to really use L1 norm. You can, and in some ways it's much more advantageous to use an L2 norm. So here's like an L2 norm definition of complexity. So now Ij is a non-negative definite matrix. So I think it should be called pseudo-norm. Then these are precisely these guys. We integrate over the whole circuit and minimize it, and we get like the complexity according to the L2. And these Ij, are just numbers, and these numbers basically what they do is they introduce weights for relative weights for different operations. So now what I described for you here is a circuit complexity of a unitary transformation. And now once one defines a circuit complexity of a unitary transformation, then one can use it to define a complexity of states. So in this transparency, I introduced for you like a proviso of how you can define complexity for continuous transformations, embedded it as a framework in a framework in which basically one calculates geodesics, in this case in a Riemannian geometry. And the remaining task actually is to understand what our generators of fundamental transformations gonna be for some interesting examples of quantum field theories, and what are reasonable ways to count applications of these generators such that the answers, say, reproduce holographic complexity proposals. So that's roughly speaking the idea for whatever I want to tell you next.
Excuse me. So you said it's like a geodesic distance, but is it, you're going to have constraints, so it's going to be more like sub-Riemannian geometry. Is that correct?
What do you mean by the constraints? You mean?
Well, your generators are you're not allowing all possible generators to, or are you?
So very good. So the key idea here is the key idea of this paper was to allow for all possible generators within a unitary group on the lattice, and then the ones that you don't want to have penalize similarly to the way I penalize here a rotation along the y direction. So that's a very important point. Yes.
So your projections or your pies are doing the job for you.
Exactly.
Sort of selecting out some favored submanifolds or something.
Exactly.
How do you know that it's consistent? Because actually when we have like geometries which are dimension like 3 and higher, it's already counterintuitive. Sometimes you can get configurations which actually don't match. So how are you sure that all these kind of constraints match together?
So as I said, like at this level there are no constraints. I mean, like we basically what we do effectively in this work, what we do is we assign a metric to a Lie group, and in the resulting Riemannian geometry, we find geodesics, and we solve we evaluate their length and look at their length and analyze the properties. So this is what we do. There is no magic there.
But you do have some kind of ambient Lie group, right? So you do have some, okay, it's in a way constrained if you have something behind, right?
So I would say that like in none of the considerations that we did, such subtleties appeared. If it's a general feature, that I don't really know.
So you're going to tell us how you choose these weights, right?
Yeah. Let me tell you, and then we can come back to this topic because I think it's an interesting topic. Okay.
Can I ask a question? You need a reference state. How do you choose it? How does one choose it? Second question is this. I suppose these are used in the boundary theory because I suppose they are quantum. Then the unitary group is infinite dimensional. So how does one define these objects?
Very good. So that these are excellent questions. Yeah. So let me go through this because like these points that you raised actually are some of the challenges that appeared to us like when we started trying to answer this problem in 2016-17. So as you said, well, when we start talking about quantum field theory, I mean, like what do we really mean by the reference state, by a simple reference state in continuum, right? What do we really mean by an elementary set of unitary transformation states? You know, like this is a unitary circuit, but you know, in quantum field theory, or in quantum many-body systems, or in quantum mechanics in general, sometimes it's really advantageous to work with Euclidean time evolution as a way of projecting to a ground state, right? Like that's how many calculations in quantum field theory or holography are done. So shall one only focus on unitary transformations, or maybe other transformations are, I mean, the Hermitian transformations are permitted at the cost that the norm of the state is not going to be 1. Similarly, do we have to consider pure states, or can we also consider mixed states? Can we come up with workable examples for mixed states? And also, I mean, like you saw on my previous transparencies that these holographic complexity proposals give rise to quantities that are infinite, because the volume of anti-disturb geometry is infinite. It's a UV divergence quantity from the point of view of field theory. So when we do calculations with complexity, how do we deal with possible UV divergences, right? So like these are some 5 challenges that I find notable. So let me try to show you how we overcome this. And what I want to say is some of your questions were really very important general questions. However, this field is an emerging field. So I think they really provide an excellent ideas for future projects, rather than something that I have a very good answer to at the moment. So like with any quantity that you like to compute in quantum field theory, probably like the best starting point are 3 quantum field theories, and in the following I will focus on 3 fermion theories that are 3 boson theories that are generalizations to 3 fermion theories as well. And what I want to emphasize is that holography, of course, in the regime where the gravitational site is described by the classical gravity theory, does not really correspond to a free quantum theory. Actually, it corresponds to quite the opposite theory, to the strongly interacting one. However, some quantities, for example, structure of divergences of entanglement entropy, is actually the same for theories regardless of the value of the interaction strength, and it largely follows from locality of quantum field theory. So some sort of a universality is what we hoped for when we started looking at complexity for free quantum fields. As you will see, actually, such a university is probably at place. So let me discuss 3 applications of this complexity. So now, what we are like the simplest thing to consider is to take your free quantum field theory and put it on the lattice. So like here is a lattice regularization of your quantum field theory. So we have some number of sites, right? These sites are separated by delta, and on each site we have, in the case of free boson theory, we have the free bosonic field and the conjugate momentum operator. And the simplest thing to consider would be to consider the target state to be a ground state of a quadratic Hamiltonian in which the mass term is, say, m1, and the reference state to be a ground state of a Hamiltonian in which the mass is m2, right? And of course, for different masses, this theory should be regarded as living in different Hilbert spaces. However, on the lattice, it's still possible to transform one ground state into the other. But of course, the overlap between these 2 states, as long as we are on the lattice and the number of sites is finite, is still gonna be non-zero. And of course, if we take the number of lattice sites to infinity, then we're gonna encounter a UV catastrophe, and these 2 states are gonna become orthogonal. But this is what it is, and let's proceed and see what comes out. Now, the beauty of this of free quantum field theory is that the ground state of free quantum field theory is a Gaussian state. And now, if we want to transform between 2 Gaussian states, we can do so using symplectic transformations. So these transformations are going to be generated by exponences of quadratic operators in fundamental variables. So for example, like the bosonic field on the first side times the momentum field on the third side, and so on and so forth, right? Now, in this, because this was the first paper, in this paper we are really guided by what's calculable, and we decided to choose a very simple metric on the symplectic group in such a way that eventually the problem of transforming between the ground state of the system with mass 1, the ground state of the system with mass 2, can be performed in momentum space for each momentum mode separately. And the answer is going to be basically the sum of the answers for each momentum mode. And it turns out that when you proceed in this way, actually the only thing that you have to do, the only thing that your circuit has to do, it has to do what's called in quantum optics literature squeezing operation. And the amount of squeezing that you have to do is going to be related to a log of the ratio of the dispersion relation for one Hamiltonian to the dispersion relation of the other Hamiltonian. So this is a genuine cost of a transformation between the ground state of two quantum field theories on the lattice. And now when you evaluate this integral and you see what you obtain, it turns out that
So I'm confused as to what freedom you have in choosing the metric on this group manifold.
You have an enormous freedom.
It's not an invariant metric you're choosing. You're just treating it as a topological space. Is that what it is? And you're not going to have left invariant and right invariant action of the group on the metric.
Sorry. I think in the approach that we have, we probably look at left invariant metrics, but this you see, like when you look at this situation, I mean, it turns out that that when we proceed in this way, I think we define, let's see, I think right invariant metrics, but what the metric is going to be, it still depends on what we choose by these penalty factors. So if we have, say, n generators, then for these n generators, we still have to specify a non-negative definite n by n matrix that is symmetric, and this filled with real numbers. And this is our freedom of defining the metric. So it's an enormous freedom.
Okay.
Can I ask one more question? A long, dangerous question. Okay.
Of course.
You're trying to intertwine two vector states. Let me call it first one as 1 and the second is 2. Okay. There is a canonical unitary which does it. Take the bracket 1, 2 and 2, 1. Okay. So the U I am writing is 1, 2, 2, 1, and the orthogonal complement of 1 and 2, I set it equal to 1. That is a unitary operator, and that is completely uniquely defined. Okay? Yes, up to a phase. So that is, you don't want that choice. I can write it down immediately, no? Because you are only intertwining two vector states.
So I think it's, I mean, you might ask a question like, this is some unitary transformation, right? So there are two things, right? So one thing is, what is the unitary transformation that does the job for you, right? And the second question is how to decompose each such transformation into a circuit, right?
Each such transformation into what?
So there are two.
Into this form. Into this
form.
There
are two things.
You want to
here,
find
right?
the Q. You want to find the Q.
So we have a target state, and to this target state we want to get by acting with a unitary transformation on the reference state. Right. So then for each pair of reference and target state, there's going to be very many unitary transformations that transform us between the two, right? So each such transformation we have to represent in terms of a circuit, And we should minimize first for each unitary transformation over all circuits according to our choice of the cost function, for example, this one. And then we have to minimize over all unitary transformations, right? So we have to perform this two-stage minimization. And only then we're going to end up with a notion of a complexity of a state.
This group sp2 and R for n finite is compact, from what I imagine. So every unitary in that representation space, if it is irreducible, is on the exponential map from the group, from the identity. So the unitary, every unitary.
This group is not compact.
This is not compact, is it?
No.
Okay, then I don't know. Okay.
It's not compact. No. So let me proceed if this argument doesn't apply. So anyway, what I was saying is that if one looks at Gaussian transformations between Gaussian state is the ground state of one quantum field theory Hamiltonian on a lattice and the Gaussian state of another quantum field theory Hamiltonian on a lattice, and you do the calculation, it turns out that well, for a particular choice of a metric on the group of Gaussian transformations, you do get an answer that in general is going to be divergent. However, if you compare the structure of divergences with what you expect to get in holography, you're going to see that there is a mismatch, so that you don't really reproduce what you want to reproduce. And you might say, okay, that's the end, right? Like the story is hopeless because you have to make a choice about the metric of the group, right? And then you have to do calculation for every choice, and very quickly it gets really complicated. And if you lose analytic control, it might be very, hard to take continuum limit and so on and so forth. However, it turns out that there is a simple replacement that you can get. So if, as your simple reference state, you take a ground state of a Hamiltonian that is not relativistic quantum field theory, but is actually an ultralocal theory, such that at every site on your lattice, there lives a separate harmonic oscillator. And these harmonic oscillators are characterized by, say, frequency squared mu. So it turns out that if this, I guess, sorry, there's a type of this should be mu squared. It turns out that in this case, if you take the result of the complexity calculation and you perform the integral, you do reproduce the result of the holographic complexity proposal. So let me repeat it because it's important. Over here, we took a quantum field theory, a free massless quantum field theory in D dimension. We put it on a lattice. We, ad hoc, you might say, define a particularly simple metric on the group of Gaussian transformations. As a reference state, we take a spatially disentangled ground state of a set of harmonic oscillators, decoupled harmonic oscillators on the lattice. And when we do the calculation of complexity, we actually do reproduce the leading divergence of the holographic complexity calculation. So when we saw it, it came to us as a surprise because, well, I mean, on one hand, holography, because holography is not supposed to work for the way I presented it for free or weakly coupled quantum field theories. However, if one think about it more, if you were to do the calculation for entanglement entropy on the lattice for a free quantum field theory, what you would see is that this entanglement entropy would diverge as the area of the boundary of subregion. And if you were to compare it with the prediction of holographic entanglement entropy, it would be the same, despite the fact that what you started with is a free quantum field theory. So this agreement that I'm reporting here, I treat as a signal that there's some universality at play, similar to the universal way entanglement entropy diverges in quantum field theory. So moving in the same way, it turns out that you can proceed to this thermophile double state. So the thermophile double state, as I said earlier, in holographic quantum field theories corresponds to a black hole solution. In the context of free theories, thermophile double state is also a Gaussian state. And as a result, like all this Gaussian machinery that I introduced for you does apply there. And it turns out that if you calculate the complexity of the thermophile double state and subtract from it twice the complexity of the vacuum in free quantum field theory, making the same choices as in this calculation, it turns out that you do reproduce this property, that the answer is proportional to the thermal entropy. So it's actually very nice, because this now we reproduce not only the property of the vacuum divergences, but also sort of a static property of the thermal or thermophile double state. And you can also do dynamics with the same setup. So, and it turns out that the dynamics does not work that well. That is, if you do the calculation with the complexity measure that we had in free quantum field theory, the complexity is a sum of oscillatory contributions. And these oscillatory contributions, they dephase with respect to each other. And as a result, complexity very quickly saturates. However, in these holographic complexity proposals, the complexity is supposed to exhibit a long time linear growth. And this we are not really able to reproduce for the choices we made using calculations in free quantum field theories. And then maybe you will be tempted to think that perhaps there are other choices that you can make, that maybe this would be possible to do. However, what we know, and this is where I make contact with the physics of particle plasma, is that the dynamical time-dependent properties of weakly and strongly coupled quantum field theories are very different from each other. So for example, and I believe some of you seen this formula already, if you calculate the shear viscosity, so a particular time-dependent property of a medium in a relativistic quantum field theory, in holography, so at large coupling constants, and normalize it to the entropy density, then what you get is a number of the order 1/10. It's 1/4 pi. However, if you do the calculation in a weakly coupled theory, so say weakly coupled QCD or weakly coupled n = 4 subprime muons, then what you get is an answer that is 1/the coupling constant to the 4th power. And as a result, this ratio actually diverges in the limit coupling going to 0. So what I'm trying to say is that there is a qualitative difference between the behavior of weak and strongly coupled field theories when it comes to time dependence. And this is something that I believe is also reflected by our calculation of complexity. So this basically finishes the part on pure states in free quantum field theories. If you have some questions, it's a good time to ask them, or if Daniel wants to proceed, I can proceed, and then I should be done relatively soon.
I think we've been asking questions as we go on this. Unless somebody has an urgent question, we can continue.
Good. So sorry. So let me summarize with some punchlines. So what we did is we consider a new quantity, a complexity, in the context of free quantum field theories on the lattice. So what we started with, basically the idea was that free quantum field theories are Gaussian, and we can use efficient machinery of Gaussian states to try to ask a question and answer the question: what is the most optimal way of preparing one Gaussian state from the other Gaussian state using limited resources, understood as putting some weight on the uses of different quadratic operators, exponences of different quadratic operators from our lattice degrees of freedom, right? So the unitary gates for bosonic theory were basically exponences of products of fundamental bosonic variables for operators living on different lattice sites. And for particular fine-tuned cost functions, we can get actually exact results about complexity. And what's important is that this requires minimization. However, if you find a circuit that does the job and evaluate its length according to a cost function, then it's not necessarily a minimum, but it gives you, of course, an upper bound on the minimum, right? Because you can always, I mean, it's possible that you can consider a circuit that gives you a lower cost, but why would you look for circuits that give you higher cost, right? If you have already this one that gives you some particular cost, right? So that's roughly speaking the logic. Now, when it comes to drawbacks of this approach, and that was related to one of the questions I obtained, is that in order to get exact closed form results without the need to do any numerical minimization, I had to use circuits that utilize very non-local gates on the lattice. So, for example, I use circuits that utilize gates in which the field operator was inserted simultaneously, you know, here at the place where I am and in the other galaxy, right? So this is something that you might say is very non-local from the point of view of field theory. So perhaps you would like to do better. And indeed, in the next transparencies, I will show you how you can do better in some sense. Now, regarding the features, the good news is that actually this very simplistic calculation was powerful enough to reproduce static properties of holographic complexity proposals, meaning leading divergences in the vacuum, complexity of formation of thermophile double states, as well as complexity of purification for subregions that I'm going to mention later. The bad aspect of it, but expected, is that Gaussian calculations provide a very different time dependence than holography for complexity, but it's not only for complexity, it's basically for any other quantity that I can think of. So it's not really worrying, it's basically there from the start. Now, seen from, you know, a broader context, the problematic aspect of whatever I describe here, or something that one would like to do better, is that these calculations do not naturally generalize to holographic quantum field theories, right? So having said what I said, I mean, it would be very nice to have a definition of complexity in a more universal example, in such a way that one can try to either apply it to a theory that is holographic, or try even to phrase it in such a way that you can be tempted to prove a holographic complexity, one of the holographic complexity proposals, right? And this is what I want to tell you in the remaining few minutes. And I will not really go very much in depth. I just want to show you like what ideas are at play. So the papers that I will be talking about in the coming few minutes are two papers that appeared this year with Mari Flory. So what we'll be considering is conformal field theory. So maybe you remember from what I said earlier about entanglement entropy. Entanglement entropy, the breakthrough in understanding of entanglement entropy occurred when people looked at entanglement entropy in the context of conformal field theory. So the idea is to do something similar, but now for this new notion of complexity, right? And to this extent, we'll consider conformal field theories on a Lorentzian cylinder with spatial coordinates running between 0 and 2 pi. So the pictures of anti-de Sitter space that I showed you earlier were precisely of, you know, the interior of such a cylinder. Now, the unitary transformation that's going to be of interest to us is going to be a transformation that realizes basically a diffeomorphism of the circle. So, you know, like from coordinate sigma, we're going to go to f of sigma, where f is the appropriately regular function. And it turns out that such circuits can be realized. Sorry, and one more thing that I want to say, so that such a function is going to be parameterized by an auxiliary parameter, like a circuit parameter, such that when this parameter takes its minimal value, so like that's in our case chosen to be 0, then it's the original coordinate. And when it takes what it's supposed to be its final value, so 1, it's supposed to be this full diffeomorphism, right? And what happens in between is some sort of a gradual way of building up a diffeomorphism, right? I mean, if f of sigma is identity, so f is identity, so f of sigma equals to sigma, then actually we don't have to do anything, right? But we're going to be interested in a situation in which this f of sigma is not trivial, and then there's going to be a non-trivial circuit that builds up. And the interesting important thing is that this whole discussion here is universal, because actually these diffeomorphisms of the circle give rise to a Virasoro group, and this whole discussion can be phrased in terms of the Virasoro group, and the complexity that one defines in this way is going to be equally well applicable to free conformal field theories, say free boson on the lattice in the language that I spoke before, or alternatively, holographic quantum field theory. And the only difference between these two calculations is going to lie in the value of the central charge, right? And all the other things are going to be entirely universal. So now the important thing for us is that such transformations in conformal field theory are generated by the stress tensor operator, so right or left moving component of the Entanglement tensor. And I ended, like, one of the drawbacks of the previous construction was that the circuits that we were considering were circuits that were formed from operators that are very non-local, right? Like we had, like, say, 5 here, 5 in the other galaxy. Now, the circuits that we're going to be using are going to be made from operators that are very much local, right? We're just going to be smearing the Entanglement tensor over the whole spatial slice, right? So that's certainly an improvement over what we did before, and rightfully so. I mean, like, this work actually was written several years later. So now I got a question about this geodesic notion. So let me come back to this on this transparency. So we did a lot with this complexity in the course of in the context of two-dimensional conformal field theories. However, here I don't want to really go into the details. I just want to show you this idea of moving in some auxiliary geometry characterized with some metric or pseudometric. So let me proceed. So we're going to be interested in a unitary transformation that represents this diffeomorphism. And our reference state is going to be an energy eigenstate in our conformal field theory. So you can take it to be the vacuum, or you can take it to be any other energy eigenstate. And a target state is going to be this conformal transformation acting on the reference state, right? So it's going to be basically some descendant state or a linear combination of descendant states, right? Maybe a complicated one. And now this is the circuit that we're going to be considered. And now you can ask a question, what kind of cost function can we use? It turns out that a very nice cost function is going to be given by the Fubini study distance in Hilbert space, right? So the idea is that as we move in the Hilbert space using a unitary transformation generated by the circuit, according to the metric on the Hilbert space, we traverse some distance, right? So this curve is going to have some length. And what we can do is we can minimize this distance. And minimization of this distance is actually a very non-trivial thing to do, because note that we're not really considering the most general unitary transformation between these two states. We're considering a unitary transformation that is only made from, restricted ingredients. Similarly to the previous situation in which we're moving between two Gaussian states using only Gaussian transformations. But you can as well move between two Gaussian states using the full unitary group. And then the story would be very, very different. So anyway, as you run the crank, it turns out that the functional that you need to minimize is going to be actually a bit complicated, but I just want to illustrate a simple point. So remember that this f of tau and sigma characterize how we perform our diffeomorphism in a gradual way. Now, as you do the calculation, what's going to turn out is that there's going to appear a 2-point function of the Entanglement tensor. So the 2-point function of the Entanglement tensor in the vacuum or in the state H in conformal field theory is given by this expression. So actually, this expression that you want to minimize looks like a geodesic motion in which, in infinite number of dimensions, in which the dimensions are parameterized by a continuous variable that is the sigma variable here associated with the position on a circle, right? So following this idea of Nielsen and collaborators, complexity is really about a geodesic motion in some auxiliary geometry that in the context of quantum field theory becomes infinitely many dimensional. Now, Mario is a very good physicist, and as a result, we are able actually to find these geodesics using certain approximations, and it's actually a very interesting problem and a very interesting project. So I refer you to our publications. Let me just quickly flash one more aspect of complexity and come to conclusions, because I think this talk is running for long enough. So I started with these holographic complexity proposals. I moved to free quantum field theories as the simplest realization of complexity in the setting of quantum field theory. And the results performed there were actually encouraging because they were reproducing some of the features of holographic complexity proposals. And now the idea of moving in the direction of conformal field theory is actually to be able to derive holographic complexity proposals, counting on universality of basically conformal group, or Virasoro group in this case, that is shared, say, between free and strongly interacting quantum field theories. Now, those of you who worked with holography know that in order to prove something in ADS-CFT, you have to use the central identity of holography, which is equality between gravity partition function and quantum field partition function, in which gravity partition function is understood as gravitational action on shell evaluated on a solution that is specified by the sources on the boundary. And as a result, if you want to proceed in such a way with complexity, what you would like to do is you would like to have the ability to assign a cost to plot the integrals in quantum field theory with particular source configurations. And this paper that we wrote in 2019 with Camargo, Jefferson, and Knaute that appeared at PRL does precisely that. So it focuses on two-dimensional conformal field theories and assigns complexity as a function of sources. And moreover, it not only, it actually mainly concerns Euclidean path integrals. And as a result, it's particularly suited for a proof of holographic complexity proposal. So over here, I'm presenting this paper as a part of mixed state considerations, because it can be applied to calculate complexity of thermal density matrix. However, from this broader perspective, it's actually about nothing else than assigning costs to source configurations in quantum field theory. Now, when you have mixed states, you can actually use definitions of complexity for pure states, and starting with a mixed state, consider a purification. So a pure state that gives the same mixed state when you reduce over some auxiliary degrees of freedom. I mean, this is something that we did in a very interesting work with Tadashi Takanagi and collaborators last month. I don't want to really dwell into details. I want to perhaps move to conclusions and later take questions. So the punchline from my talk is that complexity is a genuinely novel notion in the context of fundamental physics. So whenever I talk about complexity, I try to bring it to the same footing with entanglement entropy. So actually, if you look at this timeline for entanglement entropy, in the 80s, it was introduced in the context of quantum field theory, or like it made the major appearance in the context of quantum field theory in connection with black hole entropy. So as an idea to explain black hole entropy. This furthermore motivated development a decade later, including the first calculation of entanglement entropy in conformal field theory. Then another decade later, Cardy and Calabrese came up with a streamlined version of calculating entanglement entropy using sources in the path integral formulation of conformal field theory. Based on the universal results for entanglement entropy in conformal field theories that are enclosed in these two papers, Ryu and Takayanagi proposed how to calculate what is the holographic representation of entanglement entropy in terms of Ryu-Takayanagi surfaces. Now, almost a decade later, Lefkovich and Balacena showed how to prove holographic entanglement entropy. And now last year, Pennington and the competing group applied these ideas to show traces of unitarity in black hole evaporation, semi-classical black hole evaporation holography, right? So this is roughly speaking a timeline of the development of entanglement entropy in fundamental physics, spanning about 35 years. So what I discussed today was a survey of first works exploring the idea of complexity in quantum field theory. So if you look at the timeline for complexity in fundamental physics, I think we know much more about fundamental physics than we knew in the 80s. So the holographic complexity proposal, so complexity in gravity, is a subject of papers between 2013 and 16. 2017 is our first paper on calculation of complexity in free quantum field theories. This took us about 2 years to do these explorations. 2019 is basically introducing sources, so something akin to this paper, and studying CFT, so something akin to these developments occurred only now. So roughly speaking, regarding complexity in quantum field theory, we sort of passed like the time span of 30 years for entanglement entropy in the course of the past 3 years. It's not entirely true, but that's roughly speaking the idea. And what I want to basically emphasize is that it's not that we really have a comprehensive understanding of complexity in quantum field theory. However, there's been steady and important and exciting progress on this topic. And I believe the future for this field looks very, very bright. So thank you for your attention. And if you have any more questions, I will be very, very happy to answer them.
Okay, thank you very much for a stimulating talk, Michael. And I throw the floor open to further questions. You have covered a lot of ground here.
Okay, I have one question. You considered free quantum field theories with different masses. Now, more general, one can ask, what is the geometry of the space of all quantum field theories? And does complexity have to say something about that? For the supersymmetric ones, it's just Riemannian geometry, but in general, it will be something different.
I mean, that's a very interesting comment. I think going this direction would be interesting because it would basically free us from. I mean, I'm not sure this is something that ultimately is going to be feasible. But you see, like the way to proceed in the simple example I discussed, like this pioneering work on complexity in free quantum field theory, was basically to start with a common lattice, and in the same Hilbert space embed two quantum field theories in a sense of lattice regularization, right? And then in the same Hilbert space, proceed and calculate distances and so on and so forth. Now, if you have a geometry of quantum field theories, I mean, you might say that there is a natural notion of distance between quantum field theories, right? I'm not sure if you can think about the motion of this geometry in quantum field theory in some operational sense. But because in order to have this operational sense assigned to a geometry, what you need to have is a freedom of choosing the geometry. And by this, I mean that in our abstract considerations, what we choose as a geometry for us dependent on what we mean by simple or complicated, right? Like this is like this idea of assigning these penalty factors and saying that operations are 10 times more expensive than others. So at the core of this consideration lies the idea that the geometry for us is something that we can largely choose, and depending on what we choose, we're gonna get different answers. And even if we operate in the Hilbert space that comes with some metric, we force upon us a geometry by saying that we look at the subalgebra of observables, right? So this choice is always there. Now, in the topic that you brought into the discussion, I'm not familiar with. However, if you don't have a choice there to define this geometry in various ways, depending on your needs or the property that you want to impose, then I think this notion of complexity probably is not going to be there. That would be my superficial answer.
Okay, thank you.
Thanks for the question.
Okay. Do we have other questions? If not, let's thank Michael again, and I will stop the recording. Okay, thank you. These are very silent times on Zoom, so we're not very good.
Thank you.
Thank you. Okay,
thank you very much.
I'm just going to stop the recording, and we can.